Which has a higher temperature, the short wavelength or the long wavelength? The relationship between wavelength and temperature is complex, with both short and long wavelengths occurring over a wide range of temperatures. In general, the following trends can be observed. Inverse relationship between wavelength and temperature. Shorter wavelengths are emitted from objects with higher temperatures. This is known as Planck's law. For example, objects at higher temperatures emit mostly shorter wavelength thermal radiation. This explains why objects appear brighter at higher temperatures or why a hot flame emits higher energy light. Non-linear relationship between wavelength and temperature. The relationship between wavelength and temperature is not linear. The relationship between wavelength and temperature is complexly convoluted, so it is generally difficult to establish an accurate linear correlation. Therefore, it is difficult to determine temperature accurately from wavelength alone. Concept of color temperature. One way to describe the relationship between temperature and wavelength is to use the concept of color temperature. This is an index of how closely the spectral distribution of light from an object resembles a specific color, and it is generally higher for shorter wavelengths. For example, a candle flame has a lower color temperature and emits wavelengths closer to red, while the sun has a higher color temperature and emits shorter wavelength white light. Therefore, the relationship between wavelength and temperature is not straightforward, and it is difficult to accurately judge temperature from wavelength alone. Other information must be considered to accurately measure temperature. We know that light has various wavelengths. So is the temperature different for each wavelength? This is explained by Planck's law, which describes the intensity and wavelength distribution of electromagnetic radiation, light, emitted by an object at a given temperature. In general, objects with higher temperatures emit shorter wavelength light, and the longer the wavelength, the lower the energy of the light. This can be explained by the following key observations. Low temperature objects, e.g., candle flames, the surface of the sun, these objects emit mostly long wavelength light, which appears red to yellow in color. High temperature objects, e.g., the cores of stars, the hotter parts of flames, these objects emit mostly short wavelength light, which appears white to blue in color. These properties are also important for understanding the colors of stars. For example, red giants emit mostly red light due to their low temperatures, while white or blue stars emit shorter wavelength light due to their high temperatures. Therefore, because the energy distribution of light varies with wavelength, measuring the wavelength can provide information about the temperature of an object. This is one of the basic principles used in astronomy to determine the temperature, luminosity, and other properties of stars through spectral analysis. Additional details. The term blackbody could be defined. A blackbody is an idealized object that absorbs all radiation incident upon it and emits radiation with a spectrum that depends only on its temperature. The concept of blackbody radiation could be explained. Blackbody radiation is the thermal radiation emitted by a blackbody. It is a universal phenomenon, and it is the basis for many applications, such as astronomical observations and light bulbs. The relationship between wavelength and temperature could be illustrated with a graph. A graph of wavelength versus temperature would show that the two quantities are inversely related. The graph would also show that the relationship is not linear.